In section 6.5, we are talking about investment applications involving exponential functions. These applications are done in a very similar way to those applications in 6.4. The difference is all of them today will have to do with money. We are talking about interest and investments and loans and calculating the total amount of those investments. Let's first talk about what interest is. Interest, quite simply, is money paid on money. When you borrow money from the bank, they charge you a fee for borrowing that money. That fee is called interest. When you pay back the loan, you will pay back the total money you borrowed plus the interest that the bank charges you. Similarly, when you invest money with a bank or an institution, they pay you money for putting your money there. That money that they pay you is also called interest. So financial institutions charge compound interest on loans, and they pay compound interest on investments. Let's talk about what we mean by compound interest. When something compounds, it grows. So compound interest is a particular type of interest that is earned on both the original amount that was invested and on the interest that has accumulated over time. What does that mean? Well, let's do a quick example. Let's say that you have $100 that you are going to invest at 10% per year, and we're going to say that that interest is compounded annually or yearly, once per year. Now, when we say compounded, that means that we are taking the interest that is earned and we add it into the initial investment. So compounding means adding that interest in. Let's do a quick calculation here. If we take that $100 and we multiply it by, now we're not going to multiply it by 10%. We're going to take that 10%, we're going to divide it by 100 to turn it into a decimal. That gives us 0.1. So the $100 times 0.1 gives us 10. That 10 represents $10, which is the amount of interest earned in that year. What we are going to do now is we are going to take that interest and add it to the original investment. We are going to compound. That means now our investment is $110. When we leave that $110 in the bank and it earns 10% that year, so multiply by 0.1, that gives us $11 in interest. Because our investment was higher, our amount of interest was higher. What are we going to do with that interest? We're going to take it and add it into the investment amount. So for year 3, we have $121 in the bank account, which is earning 10%. So that year we earn $12.10 in interest. And again, we will take that interest and we will add it into our investment amount. So that's how compound interest works. The interest is added in or compounded, and so our investment becomes bigger and bigger. So anytime we say the word compounded, that tells us that we are adding the interest in. We have a formula that is specific to compound interest, and that is below. A equals 1p times 1 plus I to the n. You can see right away that because that n is in the exponent, this is an exponential function, and that is why we talk about compound interest in Chapter 6. Let's break down what the different parts of this formula are. A, it represents our future value or final amount, and let's be specific about A. A does not tell us how much interest we've earned. A is the total amount. It is the original investment plus the interest that was earned. So A is our accumulated amount, the total amount when we put together the investment and all the interest that has been added in. P represents our principal or the initial amount invested or borrowed. So for the little example that we did at the beginning there, our principal would be the $100. That was the original amount that we invested or borrowed. I is referring to our interest rate. Now we need to be very careful. I is the interest rate per compounding period. For the most part in these questions, you're going to be given the interest rate per A, which means per annum or per year. I does not always represent the annual interest rate. Sometimes the interest rate is going to change based on how often we compound the interest, how often we add the interest in. So the interest rate per compounding period, it might look a little different than our annual interest rate. N, which is in our exponent, represents the number of compounding periods. So that's how many times we add the interest in. And keep in mind, N will not always represent the number of years. We are going to use the number of years to help us calculate N, but they're not always going to be the same. Now, this looks really overwhelming, and it looks like we're learning a brand new formula, which we are, but notice that this formula should look a little familiar. In 6.4, we talked about y equals a times b to the x. This formula, the compound interest formula, is very similar. We said in 6.4 that a represented the initial amount. Well, notice that in this one, we're calling it P, and P was the initial amount invested or borrowed. B, we said in 6.4, helped us determine our exponential growth or decay. Same thing here. This 1 plus I is showing our rate of growth. It's our interest rate. And then X was often related to time, and so is N here. Let's talk really briefly about why we have 1 plus I into the base. We want exponential growth. We want our investment to grow, so we want B to be greater than 1. And the way that we can ensure that B is greater than 1 is by adding 1 to our interest rate per compounding period. But this formula, this A equals P times 1 plus I to the N, is the same thing. It's in the same form as those that we were talking about in 6.4. Having a look at this chart below, which looks a little overwhelming, it just shows us how I and N are going to change based on how many times per year we are compounding. We've already talked about compounding yearly or annually. When we are compounding yearly or annually, that means that our interest is being added once per year. And what it means is that I is just going to be the same as the annual interest rate. So this is the most simple kind of question to do when we are compounding annually, because I and N are just going to look like the annual interest rate and the number of years. What if we are compounding semi-annually? Semi-annually means that we are compounding 2 times per year. So what we are doing is it's like we are taking the year. So let's let this little box represent the year. And then we take that year and we break it up into 2 parts. We start with our money, and that money earns interest over the first part of the year. And then at the halfway point, we take our interest and we add it in. Then we earn money again on that bigger amount of money, and then we add the interest in again at the end of the second part of the year. So that's what semi-annually looks like. Well, what does that mean in terms of our I? What does that mean in terms of our interest rate? What that means is our interest rate, which is given over the entire year, is also taken and divided up into two parts. So we take our annual interest rate and divide it into two because we are taking the year and dividing it into two parts. When we are investing quarterly, that means that we are taking the year and we are dividing it into four parts. So we are compounding or adding the interest in 4 times per year. So we earn interest and then we add it in. We earn interest on that bigger amount, add it in. Earn interest again on that even bigger amount, add the interest in, and then earn interest again and add it in. So we compound or add the interest in 4 times per year. What does that mean for the interest rate? Well, because our interest rate is given over the whole year, and because we are dividing the year into 4 parts, the interest rate gets divided into 4 parts, and that's why our annual interest rate is divided by 4. When we are talking about monthly, there are 12 months per year. That means we are dividing the year up into 12 sections. That means we will compound 12 times, and it means our annual interest rate is getting divided up into 12 sections. Semi-monthly means we are compounding twice per month. So that means that we are dividing the year into 24 sections. So we are adding the interest in 24 times, which means the annual interest rate, the interest rate over the whole year, is getting divided into 24 sections. For weekly, there are 52 weeks in the year. So that means that we are compounding 52 times. The annual interest rate is getting divided into 52 parts. And daily, finally, means we have dividing the year into 365 parts, which means the interest rate is getting divided also into 365 parts. Now, let's have a look at this note underneath the chart. For Math 30-2, if the interest rate is compounding anything other than annually, so if it is semi-annually or quarterly or anything and so on, you will be given the formula. You are not responsible for creating the exponential function for those interest rates that are compounding anything other than annually. If it is annually, you will have to use the formula to create the exponential function, but if it's not, you will not have to create it. That being said, you should be able to think about this chart and understand where the numbers are coming from. Let's dive in and have a look at a couple of examples. Here's number 1. Brittany invested $3,000 at a rate of 3.5%. Again, this means per annum, which means the same thing as per year. Compounded annually. So there's the important part, compounded annually. So once per year. Because this question is one where the interest is compounded annually, we are responsible for creating the exponential function. Let's start with the formula. A equals P times 1 plus I to the power of n. A in this case is going to be our accumulated amount, and that's what we're going to want to find. P is our initial investment. Brittany is investing $3,000. We have 1 plus I. So I is going to come from our annual interest rate because it's compounded annually. What we have to be careful with, though, is we need to take that percentage and change it into a decimal by dividing it by 100. So you will have to do that, which gives us 0.035. And then our power of n, we don't know right now. We're going to leave that as our exponent. Okay, let's clean this up just a little bit. A equals 3,000. Inside the brackets here, we can add these two together. 1 plus 0.35 is 1.035 to the power of n. And there is the formula that is going to calculate our compound interest for number 1. Okay, so now what we want to do is have a look at our questions. Question A says, how much will her investment be at the end of 4 years? Okay, so at the end of 4 years means that we are given here the value of n. So n here is equal to 4. Okay, now how are we going to find the accumulated amount? We are going to do it quite simply by substituting. So our equation is 3,000 times 1.035. We are given n, so we are going to plug it in. Let's go to the calculator and let's find out what that is. So 3,000 times 1.035 to the power of 4. And there's our answer. Now keep in mind that this value right here is the total amount of money that Brittany has. The total amount. It has her original investment along with the interest added in. Also, because we're talking about money, we're going to round to the nearest hundredth, so we have dollars and cents. So her total amount is $3,442.57. Let's look at part B. How much will her investment be worth after 6 complete years? Okay, we're just given a different value of n. We're going to approach it the same way. We are just going to substitute in 6 for n. So 1.035 to the power of 6. Back to the calculator again. 3,000 times 1.035 exponent 6, and there's our total amount, $3,687, and again, rounding to the nearest hundredth, 77 cents. So 3,687 and 77 cents. And don't forget your dollar sign. That is our units for this one. Part C. How many complete years will it take for her investment to reach $5,000? So in this case, we are looking for n. We know the accumulated amount is 5,000. So we are not just substituting. In this case, we are solving an exponential equation. Our A is 5,000. So 5,000 equals 3,000 times 1.035 to the power of n. We need to solve for n. Just like in 6.4, we know how to solve equations of this type. We are going to solve by graphing. I am going to put my exponential function into y1. I'm going to put the value I'm trying to find into y2. And we are going to have the calculator calculate the intersection point, keeping in mind that we only need the x or the n value of that intersection point. So let's go to our calculator. Let's go into y equals. So in here, I have 3,000 times 1.05 to the power of x. That was our exponential function. Into y2, I've put our value of 5,000. Now, before we graph this, we have to make sure that our window settings are going to actually show us that intersection point. For the window, I have set my X minimum at 0. X is representing the number of years for the investment, so we can't have a negative number of years. I let my X minimum be 0. And I set the X maximum at 20. And again, I'm just sort of guessing. We can see that for 6 years, we only got to 3,600. So we're going to have to go a little bit higher, quite a bit higher, to get all the way to $5,000. So I set it at 20. My Y minimum, now the minimum value of this investment is going to be $3,000 because that's how much she invested at the beginning. And then we know that the amount of the investment is going to go up from there. I set the Y maximum at 5,500. I knew I would have to go at least as high as 5,000 because that's the value of Y2 we're going to put in there. And then I just went up a little bit from there, but 5,000 would have worked as well. When we graph it, the blue graph represents our exponential function. The red graph represents our Y value. We want to find that intersection point. Second, trace. Number 5 for intersect, Y1 enter, Y2 enter, and then guess enter. Our intersection point again, just look at the X coordinate, is 14.85. 14.85. So let's go back and put that in there. N is equal to 14.85, and our unit is years. If we go back, though, and read the question again to make sure we've answered it, the question says, how many complete years will it take for her investment to reach $5,000? So even though we will have to round up here a little bit and she'll be beyond 5,000, we will, in fact, round up. So we're going to call this 15 years. If we said 14 years, she won't quite get to the 5,000. So I know that if we wait for 15 years, she's going to be over 5,000, but we want her to get to at least that amount. So we're going to round it to 15. Okay, so because it was a compounding annually question, we used our compound interest formula to calculate our exponential function. For A and B, we were given an N value, so we just substituted. For C, we were given an A value, and we solved by graphing. Let's look at number 2. Carlos has been given a gift of $5,000 after graduation, $500. He can invest this at a rate of 6% per annum per year. Oh, but look at this one, compounded monthly. So this is a question where it is not compounded annually. The value of this investment can be represented by the function A equals 500 times 1.005 to the power of 12n. We are given the exponential function in this case because the interest is not compounded annually. Let's look really quick, though, at how we can see where this formula came from. A equals, well, we can see that, I'm going to write it down here. A equals 500 times 1.005 to the power of 12n. We can see where the 500 came from. P is our principal, the initial amount. That's how much money he started with. Now the 0.05 looks kind of weird because we have here that it's 6% per annum. But because it's compounded monthly, in order to find that I value, we're taking that 6% and we are dividing it by 12. So that's where that 0.05 is coming from. And then we divide it by 100 to get it as a decimal, and then 12n. The 12 is again coming from 12 times per year. So even though we're not responsible for creating that compound interest formula, we should be able to understand where the numbers are coming from. Okay, A represents the accumulated amount, N represents the number of years Carlos invests for. Determine the amount of compound interest earned if he invests for 5 years. So again, we're given an N value. All we need to do is substitute. A is equal to 5,000 times 1.005 to the power of 12 times 5. And that 12 times 5 is in the exponent. So I'm going to go to the calculator and I'm going to put that in there. Whoops. So 500, times 1.005. And then to the power of, now I can do a couple of things here. I can actually put in the 12 times 5. If you have an older calculator, make sure that 12 times 5 is in brackets. Or I can recognize that 12 times 5 is 60 and put 60 in the exponent. There is the total amount of Carlos's investment, $674.43. So $674.43. There's his accumulated amount. Again, let's go back and read the question. The question says, determine the amount of compound interest earned. So this question isn't actually asking for the accumulated amount, but how much interest they earned. To find how much interest, what we're going to do is take the total amount that he has, and we're going to subtract the initial investment. That will tell us how much interest was earned. So we're going to take the $674.43. We're going to subtract the initial $500 that he invested. That means the amount of interest that he earned was $174.43. So really read the question carefully. If this was just asking for the accumulated amount, we would be done here. But because it's asking us for the interest, we need to do that extra calculation. All right, so those are the exponential applications for financial or for investment questions. Again, compound interest formula, very much related to the interest formula or the formula that we talked about in 6.4. Now it is your turn to go ahead and practice these questions.